Myself, Dr. R. Jana from the Department of Chemical Engineering, Holding Institute of Chemistry, would like to discuss on the topic transfer operation 2. This course is designed for especially for biotechnology. Now, today we'll discuss about the dialysis process. A process for selectively removing low molecular weight solids from a solution by allowing them to diffuse into a region of lower concentration is called a dialysis. That is, the solute will move from a higher concentration to the lower concentration. This is the natural rule. So from higher concentration to lower concentration, the molecule will move. And this is the process actually. So principle is like that. There is a little or no pressure difference across the membrane. In my earlier tutorial, we have discussed for different membrane operations. There requires different driving forces, and here actually it is the pressure difference, and its pressure difference is very low. We'll discuss in detail what will be the limit of the pressure in the next few slides. Now, as the principle, the flux of each solute is proportional to the concentration difference. Solutes from high molecular weight are mostly retained in the feed solution because of their diffusivity is low. So the concentration here limit is very less one, and most of the cases micrometer like that. So let us consider the principle of this and the dialysis mechanism. There are say different solid concentration, maybe Ca, Cb, Cb, Cc like that way. C means A and B, that is the different solids, and A is having higher concentration, and B is the intermediate, and C is the colloid molecular structure. So definitely through the membrane, when that solute will move first, then the low molecular weight component A will move first. Then so there is the gradient of the concentration that is showing in the diagram. So in the right hand side, the mixtures with different solutes with different concentration are showing CC, CB1, CB, HBA1 like that. This is the feed part. And then get the boundary layers being formed actually after the passage of sufficient time. The solutes, they are maybe deposited on the membrane side, and they are forming a resistance against the flow. So that is the boundary layer. So that the concentration gradient will be there, and after that the solute will pass through the membrane, and it will permeate through that, and ultimately we will get the product. In pore fluid and the product species, it is actually zero. You can see on the left hand side, the product size, there is no concentration of C, that is colloidal particle. The main purpose of the membrane separation is to separate the colloid particle. So it has been done. Now solid flux J, it is defined as the K into Ca1 minus Ca2, where that K1 and K2 are the membrane coefficient for the feed product. They are dependent on flow rate, physical properties, and membrane geometry. So the membrane coefficient that depends on the effective diffusivity. So Km equals to d by z, and there is also equation for the effective diffusivity like this one. D equals to dv epsilon tau 1 minus lambda square into 1 minus 2.0104 lambda plus 2.09 lambda square minus 0.9 by lambda cube. These are the empirical relationship to estimate the effective diffusivity. And as you know, the lambda is the ratio molecular size to the pore size, and 1 minus lambda square, there is a volume fraction available for a spherical molecule. And the second term here, which is actually representing the hindered diffusion term. dV is the volume diffusivity, epsilon is the membrane porosity, and tau is the toxicity of the pores. So from here we can estimate the membrane coefficient Km. Now application of the dialysis, as we have discussed earlier, for the problem if they are in kidney, we can do the dialysis. It acts as the artificial kidney to remove waste product from blood. Hollow fiber cellulosic membrane are employed and blood is passed through the fiber while saline solution is circulated on the other side. So urea and other small molecules diffuse through the membrane to the external solution while proteins and cells are retained in the blood. So by this analysis process, the unwanted material such as urea, other material are creating so many things are there. Sodium chloride, sodium chloride. We are going to take them out from the body, but the protein and other essential nutrients may be retained in the body. In the schematic diagram, it is showing that the modern instruments are available for dialysis purpose. We'll discuss the details in process of the dialysis later on. Okay. Now, the recovery of caustic from hemicellulose solution produced in making rayon in viscous process. In that process also we can use the dialysis. Flat sheet membranes are placed parallel to each other in a filter press, arranged, and water is passed countercurrent to the feed solution to produce a dialysate with up to 6% of sodium chloride, sodium hydroxide. Recovery of salts or sugar from other natural products would be achieved by dialysis also. Many large-scale applications of electrodialysis used in ion selective membranes and a potential gradient to speed on ions through the membrane, that is also used. The electrodialysis is a special type of dialysis where electrical charge membranes are used. Here is schematic diagram. From the bottom we can see the feed and the membrane. We have different charged independent. We are having selectivity, cation exchange region, and anion exchange region or membrane. So A means anion. Here it is showing here. It will pass through the anion whatever the solution in the anion position with that will permeate. But in cation formation membrane, okay, the cation will permeate, but anion will be rejected. So in a solution, say for this chamber, the concentration of anion will remain same, but the concentration of cation will increase. And in other chamber, say anion will here anion will decrease and cation will increase. So if they are reacting each other, we can get desalinated water, that mainly hydrogen and hydroxyl ion, they combine each other, they form desalinated water, and from the other side we are getting concentrated brine solution, which is mostly using the separation of saline water. So the principle is that the cell is divided into number of compartments by placing pieces of cation exchange membrane and anion exchange membrane. At the two ends, the cathode and anode are connected to a DC power source. The feed solution containing sodium chloride flows through the compartment. Let us consider one of the components, that is sodium ion, passed through the cation exchange membrane, where anion are written through other membrane partition in the compartment. An anion exchange membrane allows the anion required ion to pass through. We have explained earlier actually. So the applications of the dialysis may be in various fields. It is used in desalination of brackish water. It is used to concentrate seawater up to say 200 gram per liter salt prior evaporation and crystallization for production of table salt. It is also used in recovery of nickel salts by concentrating the electroplating range water. This technique is used with food industries to demineralize cheese, which contain about 6 to 8% of salt. In combination with this mixed-phase ion exchanger, the production of ultra-pure water for semiconductor industry may also be used. So dialysis has a wide application, and it is nowadays also used in different applications. Now coming to more details about the hemodialysis, this schematic diagram is showing that from the body, blood is taken into this dialyzer, and there is online more concentration measuring devices. And there are different sensors attached. Maybe say A is the urea sensor, here B is the pH sensor, C is the middle molecular sensor, D is the pressure sensor, C is the micro pump here. So from the body, blood is coming into the dialyzer, and it, as I mentioned earlier, different movements are used. You can see from the above schematic diagram. The dialyzer with the essential nutrients is going into the body, and the blood, it is being dialyzed, and dialyte is coming out. So dialyzed blood is going in that side diagram into the body. So this is the next one here. I'm not going to discuss my line here. Already, what to say. As I mentioned, say it is used for say dialysis if there is a more concentration of impurities in the blood and kidney is not effective for that case. Hemodialyzer it is used. The first successful hemodialyzer was constructed in 1945 by Pope and Bach. They used a cellophane membrane for the purpose. A common device frequently used in hemodialyzer consists of bundle of hollow fiber membranes coated with polyurethane epoxy agents at the two ends and fitted in an outer polycarbonate housing. So device is a cell and tube type construction and is fitted with nozzle connections. The blood drawn an artery of patient's body is passed through a PVC by a peristaltic pump to enter the lumen side of the hemodialyzer. And an isotonic aqueous solution that is containing glucose and electrolytes, which are essential for the body, we are passed into and counter current flow of blood and dialysis is usually maintained. Purified blood flows back in vein, and the positive, that pressure difference it is about 100 to 500 millimeter of mercury is maintained. The most of the cases that operation is being controlled by computer. Hollow fiber typically it is having say 200 micrometer ID and 10 to 25 micrometer wall thickness. The common membrane material are generally regenerated cellulose, the cellophane or cupraphone has cooked as made by the cupramonium process, cellulose acetate, polysulfone, polyacrylonitrile, polyacrylamide, polyamide. These are the different polymeric material they are used commonly for this dialysis of the blood or other solutions. Although nearly half of the dialysis venues have cellophane membranes, microporar asymmetric hollow fibers, the skin layer on the inner side in the contact with blood are being preferred because of higher permeability. There is the molecular range of the molecule, maybe 1000, and the typical hemodialyzer has a surface area of 1 to 1.5 meters square, length of 25 centimeter, diameter of 5 centimeter, number of fiber maybe 6,000 to 10,000, and about 60 to 100 milliliter blood fills the dialyzer. Hemodialyzers are produced in huge quantity, over 70 million annually, and account for the largest share of the membrane bucket. So these are the different theoretical analysis for the hemodialyzer. Ultimately, we can show that the number of mass per unit, that is KL AM by QV, the transfer coefficient. AM is the area in membrane and QV the volumetric flow rate of fluid. So from the analysis, we can get that the time for dialysis, that is VN by QV, telling C1 by C2, 1 minus e to the power minus nt to the power minus 1. Solution concentration, initial stage, and concentration final stage, volume of the blood to be dialyzed and volumetric flow rate. So how much time is required for the dialysis process, we can estimate using this equation. This is a very essential equation and most of the cases we generally use it. Okay, we'll discuss later on this one and two.